Greetings and welcome to a new video about 2 degrees of freedom PID controller design. This will be our example number 4. In this example, I will again step by step work out the calculations with you and we will verify these in MATLAB simulations. Okay, let's look at our example number 4 and also the given system here. Again, we have an open loop system, which is also called a plant in a 2 degrees of freedom control system as shown here. So 2 controllers, the plant, the reference, the disturbance, and also the output, again in the similar configuration as in example 3. The plant is in this case very simple expression 1 over s squared. So this will be of course also worked out step by step. This will be of course also a little bit special because we have 2 poles only at the origin. So let's see what we get. Now we have the specifications as shown here. Response to a unit step disturbance again must be small, has a small peak, and it settles to 0 in less than 2 seconds. Again, this is most of the time the case also in the previous examples. The response to a unit step reference input has a maximum value of the overshoot of 5% this time. So that is the lowest overshoot we now have in these series of 2 degrees of freedom control systems. And the settling time is again 1 second. The steady state errors for step, the ramp, and also the acceleration reference inputs must be 0. So these are the specifications. So let's look at the solutions. Again, we start with the closed loop transfer function. First with the disturbance to output, so only considering the disturbance. This will give you this expression. Again, the plant over 1 plus the controller combination times the plant. So this is again the characteristic equation for this. And if I look at the reference to output, so only considering the R, so no D, then you will get this expression. So again, similar expression we have seen in the previous examples. We can also define an expression for the total controller. So the controller G of C is controller 1 plus the controller 2, which is actually shown here. So that will be of course then easily written in this form for both cases. So disturbance to output and reference to output. Now you can also write this down in this form. We've done this also in example 3. You can see we can recognize this expression G over 1 plus GC. G is actually also shown here. Okay, now let's start again assuming that the total controller expression we have here, so actually here in the characteristic equation, is a PID controller of this form. Again, a controller and just a 0, 1, 0 location given of course, but 2 zeros at the same location. So we have 2 zeros at the same location and 1 pole. So that's the transfer function for our total controller, PID controller. Then the root lowest equation is given by 1 plus the loop transfer function is 0. So 1 plus the controller times the plant will be 0. So if I now substitute everything, this will be the result. So any addition here is just the 1 over s squared. And this is the controller, and you get this. You can see already that this system has 3 poles at the origin and 2 poles at minus A. This is interesting. You might ask, okay, this 3 poles at the origin will of course cause some extra specifications, or maybe the response at the steady state values. We know that for type 1 and type 2 type of systems, we have 0 steady state errors for step, ramp, and the kind of response. So let's check this in great detail later on. Now from the specifications we have this, so the MP was 0.05 or 5%. Now going to the formula again, you will get 0.69 for the damping ratio zeta, this one. Now the settling time is 1, so 4 over the settling time will give you the sigma d, which is the absolute damping. Again here the 4 radians per second as in previous examples. Now then the imaginary value, because this will the real value, imaginary value is this. You just substitute the values we have here, we'll get 4.2 radians per second for omega d, which is the imaginary value of the design point. Design point given here in general form, PM is equal to minus sigma d plus j omega d. Substitute everything we have, minus 4 plus j 4.2. This is an important step again. once we have this, we can move on with the root locus equations and the separate steps. First was the angle condition. Again, we draw a sketch, so we make a real and imaginary axis, and we look at our PM, the design point, and here we have the design point designated with the imaginary value here and the real value, so it is the PM. We also know that this is our root locus equation. 1 plus the k, s plus a, quantity squared over s cubed is equal to 0. We have a pole at the origin, of course, but we have 3 poles actually at the origin. So 3 poles at the origin, they will be had at phi 1, phi 2 and phi 3. So all of them have the same angle. So 3 poles at s is equal to 0. That's actually what it is. In this case, of course, we have also the location of the 0. We don't know yet where it is. So let's first calculate that and then make a good estimate for the sketch. This is then the angle condition. We can see here minus phi 1, minus phi 2, minus phi 3, because the poles will have negative phase contribution and the zeros will be positive phase contribution. Since we have 2 zeros, again, we have plus 2 times that phi a will be then minus 180 degrees. Phi 1 is the phase contribution of the plant at 0, s is 0. And again, the same plant as pole, so we have done 2 poles at the origin. Phi 3 is the pole at the origin due to the PID. And we have the phi a, which is the phase contribution of the double pole, double zero of the PID, which is then at s minus a. Now, phi 1, phi 2 and phi 3 are all the same. So we can say, let's do that at once. So it is then 180 degrees minus the arc tangent of this part, so which is actually 4.2 over 4. That will give you this angle, this sharp angle. You then do the following: 180 degrees minus this part sharp angle will give you the angle here, which is then of course larger than 90 degrees, between 90 and 180 degrees. So that will be then 134 approximately. Now we have now the phi 1, phi 2, phi 3. I will then insert that in this expression. 3 times actually minus 134 plus the 2 times the phi a will be then minus 180 degrees. Now I need to know what the phi a is, just one phi a. That will be 111 degrees. So that's the result here. Then what? Okay, this is here. We don't know yet where it is, but it is already, of course, larger than 90 degrees. So somewhere here, just as estimate, of course. Now we need to calculate also the actual value. So let me first draw the location. This is then the 111 degrees. And that's the double PID 0 at s minus a. Then we get the following. Again, you use this sharp angle, the smaller angle here, in the tangent formula. So the 180 degrees minus this angle will be then 4.2 divided by this distance, which is then 4 minus a. And if you now do the math here, you just substitute the values we have and you will calculate 2.4 approximately for a, or 2.39. That's the a. So we know it is now here approximately. Then the total controller of the PID controller now is given by this expression. We don't know the controller gain yet, so we need to calculate that. So that is then the situation here. Okay, this is exactly the same, of course. All right, moving on. This is then the plot again. So the magnitude condition, this is the next step. In order to calculate k using the root locus equation, once again the root locus equation, you substitute everything in it. You make it simpler, or actually write it down in a simple way, and then you express the k value in the rest of the parameters. So you isolate k. K is then this expression. Now you can now do the following. You just substitute everywhere where you see s, this PM, which is actually our design point. Now this is what you get. You can see everything which is made red is now shown here, and now I need to, of course, simplify this. This is, of course, minus 4, that's the real value, plus 2.39 will be, of course, minus 1.61. And if I now want to calculate the magnitude of this one, you can use again the standard formula for the magnitudes. Remember, this must be, of course, cubed, and this must be squared, so you will get 9.46. Now then the PID controller, the total controller, G of C will be then this. Of course the K is unknown, so I just write it down, will be this. So we have the PID control, total controller, which was actually this one. This can be also written in this form. So what we actually do here is 9.64 again as a parameter or a coefficient in the front, and this will be worked out, so the parentheses here, so you will get s squared plus 2 times this times s, and then this squared, so 2.39 squared. The result is actually here, and you can of course also multiply the 9.64 with each of these terms in the numerator. If I now work this out and divide everything by the s here in the denominator, I will get this. And what you recognize here is the p, the I, and also the d. So this is just a gain, this is an integration 1 over s part, and this is the times s. So this is the differentiation. So p, I, d. So you can see that this is indeed the similar form of a PID transfer function. Now the closed loop transfer function for the TYD, which is then from disturbance to the output, will be then this. This is of course what we have given already. Now if I now substitute everything in it, we have now determined our PID controller. What we have is then just simplifying this, you will get this. Now even more simplification, because we want the denominator as a polynomial that we can use later on in our zero placement approach. We have discussed this also in the previous examples. You will get this. You can see it's a third order polynomial, and the s is still in place in the numerator. So the step from here to there is, I think, straightforward, but let me remind you again. I will multiply the numerator and denominator by s cubed. So I will have s cubed here, 1 times s cubed, and the rest is of course what we have here. Okay, moving on to the next step, which is then step 2. Now we consider only the reference signal. In this first step we considered only the disturbance. Again, a closed loop transfer function. We can see this is the only part which will be added here in the numerator. The rest is actually the same as for the disturbance to output transfer function. Then we have the following, just add everything what we have. What you get is then this is the planned transfer function for the controller, etc. This is then the result. So only addition is just this. So this is exact same characteristic equation, or the denominator for TYR is the exact same as TYD. Now, next step is the important step is the zero placement approach. What you then do is you choose to denominate the numerator of this transfer function be equal to the last 3 terms of the denominator of this expression. That means actually following thus GC1, which is the controller 1 times this s, it will be then 9.64 s squared plus 46.1 s plus 55.1. Now in order to calculate or to express this controller 1, you just divide by s and you will get this. And what you recognize here is the following. You can of course rewrite this here, so you can make this expression from this, and this expression is actually what we already saw in the total controller. So the total controller will be then used in order to calculate the controller 2. What is controller 2? We know controller 1 plus the controller 2 is controller total. So controller 2 is controller total minus the controller 1. This is what we had already for total controller, total PID controller, and this is what we now have for our controller 1. Now what does mean is actually this is just 0. So that means the following, which is very interesting, and we actually had a feeling that this plant with this 1 over s squared will provide or maybe have some special effect here to the responses and also for our design of the controller in this configuration. So we do not need any controller, so there is no need for a second controller to meet the specifications in this configuration. And that's actually what we had also seen in this plan. So actually this is due to the plan. The plan transfer function is determining that we don't need this. So moving on to the total result, what we have, we start with this. This will be of course gone. So the total controllers were this. So this is the first and this is the second one. This is 0. This is of course also the total controller then. And then this will be of course this, because there's no controller. So then this will be then just unity gain feedback, because I don't have any signal in it here. So this is just this. And these two summation points will be then merged together, and you can make it actually like this. This is controller 1 actually, but this is of course also the total controller. So that's for our system. Now let's look at the simulation result and looking at the unit step responses. This is the unit step response of the disturbance input, so unit step disturbance, and also the unit step reference input. So I will take them together. You can see the blue line is for the disturbance, which is very small actually, and the orange line is for the reference. You can see it, I have overshoot and also the settling time and also the final values. Now let's see that one by one. Now we know the specifications are again shown here, and if I now look at my step reference response, I have 25.8% overshoot, which is of course much larger than 5%, and I have 1.36 seconds, again much larger than 1 second. So again, both specifications are not met. I have of course my final value of 1, so steady state error is 0. That is fine, but I have 2 problems, so I need to fix that later on. Now looking at the response from the unit step response, I see this. So this is much larger than 5%. Again, the summary here, so I have 2 problems. Looking at the response due to unit step disturbance, I have this, which is 0.0192 as the peak amplitude at this time, which is small. If you just apply 1, you get for example 0.02, just 2% out of it, which is not that much. And this again very close to 0 actually already in 2 seconds, which is what we have also from the specification. So disturbance disturbance response is doing what is expected or what is actually required, but the step reference response is for the overshoot and all for settling time definitely not what we want. So we need to also look carefully and actually tune the controller later on. Let's also look at the root locus. We also know that we use this configuration in the MATLAB. So we have C1 and C2 again in a combination. This is the plant, and this is just assuming 1 because there is no feedback element here, and the noise is considered as 0. This is the part for the root locus where the C1 gain is changing, and this for the C2 gain is changing. Since this is 0, of course, this is not doing much at the moment. And again, you can see the same values here for the overshoot and also for the settling and also for the final value. So we can see we need to fix this, and you can also see the same for values for the disturbance. So this plot will give you, of course, another way the information what we have seen in the previous slide. So we need to tune the controller again. So that's what we need to do. What we do always, and I always propose and advise you to start with the easiest way. Let's also check the original designed controllers. Again, this is what we had, and this is what the controller 2 was. This is for controller 1. I have the gain here and I have the 0 location there. So what we can do, after trial and error, I have actually looked at changing the parameters for the controller 1. I said, okay, let me change the gain. I have increased that from 9.64 to 78.7. Just looking at the gain root locus plot. Let me go back in order to show you this. This here I have actually used, and by looking at this pink dot, and if I move this with my mouse in the controller designer application of MATLAB, I can then increase or decrease my gain and then change the controller gain, and then it will of course then reflect this response directly to in this case here. So moving on, that is actually, let me go faster. So this is then adjusting this, and that makes the controller 1 this. So I have only changed the gain. The rest is the exact same. The 0 location is the same. I don't change any poles, etc. or add any poles. Now that means actually the controller will be this, controller 1 actually also. So the disturbance, etc. will be all the same, and the plant is always also there. Now let's then look at the root locus and the responses, so the total situation. This is of course due to the change of that pole, and this also changing together. What you see is actually here 4.99%, and also the settling time, so, and the final value. So these are all fine. So settling time is here 0.313 seconds, much smaller than 1 seconds, and also 4.99. I have actually of course tuned such that I am at the 5% approximately, so this is also fine. This will of course meet specifications, and we see also that the disturbance, the peak value, also decreased because it was actually much larger compared to this what we have here. So again, less than 5%, less than 1 second for the settling time, and also steady state error is 0. Here again, smaller peak value for our disturbance, again a win-win situation. And also you can see at 2 seconds it is not that not 0, but still very close, approximately 2 times 10 to the power minus 4, so very small value for disturbance by just tuning or change the gain of that controller 1. Now looking at the unit ramp response, because that was also important, the results there, what we do is, now let me check that in the orange line is the input and the response, the blue one. So you can see here at 0.2 seconds, so actually at the beginning, I did it actually purposely. You can see still some difference between the actual ramp and also the response. So it is actually 0.005 difference, but you will never look actually at the response in the early stage. So you will actually wait a couple of seconds or maybe longer depending on the system, and then decide for yourself if there's a ramp error or not. Now if I look at 1 second, I have a 1 as an amplitude for my response, and also the ramp is 1, so there is no error here, so there is no difference. Now if you move up, it's exactly the same, so you will not get a 0, you will not get any steady state error. Now looking at the specifications, we need 0 steady state error for ramp, and we have this, and this was the transfer function, and this is fine. Now looking at the acceleration response, again the plot is shown here, the orange line and the blue line almost almost not, you cannot discriminate that, so it's actually on top of each other almost, but you can see again at 1 second here I see 0.5 for my reference input, but my amplitude for my response is 0.499, so not 0.5 but close. But again, don't look at it at the early stage, so if you go further, let's say at 1.6 seconds, it is an amplitude of 1.28 and also 1.28 for my response. So you can see, again, looking at the specifications, I have 0 steady state error for acceleration input, and that is actually what we wanted. And again, we meet the specifications also for ramp and acceleration response, and this is the transfer function we have used here. Now let's compare the results using the reference to output. This was the orange, was actually the response using the originally designed controller, and this is the response we have by tuning the controller gain. This is of course bad for settling time and overshoot, and this overshoot here is better, and also the settling time is much smaller than 1 second. And also the final value for each case is 1, so that's always okay. And this is the result. You can see here that we have the controller 2 always 0, and you see that we meet the specifications in the column here for the tuned controller. Just tuning the gain, that's all. Okay, moving on to the disturbance. Again, in similar form, the orange one is the original value and the blue one is the tuned. You can see the peak has decreased a lot, so from 0.02 approximately to 0.02, so almost 10 times, which is a lot. And the decrease also in the value at 2 seconds, because that was one of the specifications. You can see this is much higher than that one, so it is fine. And this is also much smaller than that one at 2 seconds. So comparing the original designed controller and the tuned controller specifications, peak value here, you see it's much smaller, and after 4 seconds, and it's after 2 or 3 seconds. So you can see in total that tuning the controller, just the gain of it, just one parameter, actually made the disturbance response better, but also the reference response for the step also much better, and also within the specifications. Alright, this was for example number 4 about the 2 degrees of freedom PID controller designs using specifically the given configuration. And in this case, we have seen that the planned transfer function has an effect on using controller or second controller or not. So you don't need a second controller necessarily. It really depends on the configuration and also on your planned or other parameters in your control system. Alright, this was for example number 4 again. If you have any questions, just let me know in the comment section. I will try to answer them as soon as possible. Thanks for your cooperation. If you like the video, please give me a thumbs up and share the video so that we can reach more people. Thanks for your cooperation and see you next time. Take care.